Howdy y'all, welcome back to the channel. I am Professor Parks, and this is another one of my lectures in my series on the solar system. Before I begin though, I'd like to kind of address this in a kind of a weird way, in that so at observatories we frequently get asked to do things beyond the normal tours. The main thing that the main sort of thing I'm thinking of is wedding proposals. So we get a fair number of people who contact the observatory to use it as a way to propose to their significant others. Well, this time around, coming next Friday, we are actually going to have a beer launch party for Aslan Beer Company, which is a local brew here in the DMV or the DC, Virginia, Maryland area. And so that reminded me of your light beer joke, or light year joke, reminded me of the fact that, yes, we are actually hosting a beer launch party here at the observatory next coming Friday. So if you're over 21 and you're in the area and you want to sample a new beer called Clear Nights, come on by. But anyway, I digress. This is supposed to be serious business. It's supposed to be a serious astronomy lecture, which Georg, I think I got that. How do you pronounce that? Georg? Hope so. I was talking about light the last time we were together. I was talking about the fact that astronomy owes most of what we know about the universe to our analysis of light, of specifically how light interacts with matter. And I talked about things like black body curves. I talked about the Stefan Boltzmann law, Wien's law, that sort of thing. Not so much. Not so much. Parsecs is is distance, not a time, but we'll give it to him. And so gave you those laws, and I talked about specifically the spectra, the astronomical spectra that we observe. Kirchhoff gave us 3 laws, which basically said that if you have a very hot, very dense object, the light that streams off of that object, or the light that emits off that object, if you pass it through a prism, is going to be what's referred to as a continuous spectrum, a rainbow pattern of color ranging from red wavelengths through to blue wavelengths. But he also told us that if you take that continuous source, if you take the light from that continuous source, that hot, dense object, and you pass it through a cloud of gas that is cooler, not necessarily cold, but cooler and less dense, then what you'll find is what we refer to as an absorption spectrum. What you'll see is a rainbow pattern of colors with dark lines running through it, vertical dark lines spaced out over that pattern. And the dark lines indicate to us that some of the light that is coming from that hot, dense object is getting intercepted by that cloud of gas, getting absorbed, and then re-emitted out into space in random directions. And we know it does get radiated out in random directions, because if we look at that same situation, but we don't look at it where it's cloud and source, but we look at it kind of like over here, where we're looking directly at the source, but we're looking directly at the cloud, but not at the source. What we see is those lines, those dark lines, the light that we couldn't see when we were oriented this way, we can now see an emission. So the background is flat. So we don't see a lot of light, but the light we do see is exactly in those wavelengths that we could not see when it was in the absorption spectrum. So, what I'm going to go over today is sort of the physics, as it were, of how that occurs. Why do we have those Kirchhoff laws? Why do we have, or rather, why do those Kirchhoff, or how do those Kirchhoff's laws apply? How is it? What physically is going on that allows that those laws describe? Not really saying that very well, or at least not for me. But hopefully it becomes clear. Now, I say that I'm going to show you sort of the underlying physics, but I also have to admit that what I'm going to be showing you is really just kind of an approximate picture. Because when we start talking about the atom, when we start talking about subatomic particles, things get a little wonky. And by wonky, I mean quantum mechanics. So prior to quantum mechanics, prior to the full treatment, Clive could probably help me out with whoever actually came up with this, but we had this idea of what an atom is. And Niels Bohr came up with the idea that put together this model that suggested that the nucleus, the positive nucleus of an atom, lies at the center, and then surrounding that are the negatively charged electrons. Now, the Bohr model, which is inaccurate in reality, if you want to put it that way, but the Bohr model looks very much like a model solar system, where I keep hitting that button. And if we go to ye old Wikipedia, I'll show you what I mean. Whoops. So if you go to the Wikipedia, it's basically going to show you this. And so the idea here is you have, what Bohr stated was that you have the nucleus of the positively charged nucleus of the atom. It's at the center of things. And then around that, you have these electrons that orbit around at certain distances, very much like planets orbit around the sun. The main caveat, the very, very important caveat to this, is that unlike planets, which can theoretically orbit at any distance away from the sun or of their host star, electrons can only reside at certain distances, which we refer to as energy levels or orbitals. That sort of carries over from the Bohr days. Call these areas, I guess, as orbitals or energy levels or what have you. Because what Bohr tells us is that energy is quantized, or what Planck tells us is that energy is quantized. That energy, that these electrons can only reside in very certain discrete energies. That an electron for a hydrogen atom cannot exist anywhere. It cannot have an infinite range of energies. It only has very specific energies at which an electron can reside. Or in the Bohr model of the atom, that corresponds to orbits, or these circles that you see here. Hopefully you can see my cursor right now. And we'll get into that a little bit more in a second. That's really what I'm going to be focusing. I'm going to be using the Bohr model of the atom in order to explain phenomena such as absorption of light and emission of light. Now, in reality, if you want to get really picky about it, then what is the atom? What is our best picture of what the atom actually looks like? Well, like I said, that gets a little complicated. But this is from the Khan Academy. In essence, you have a gentleman by the name of Heisenberg, who has nothing to do with math. Heisenberg talks about the idea of the uncertainty principle, that if you have a particle in space, you cannot precisely know both its position and its velocity at the exact same time. Or you cannot know its specific energy and its specific energy at any specific time. There is an inherent uncertainty built into the universe. And so instead of a discrete orbit, as it were, that the electron is sort of going around the center of the atom, we still have the positively charged nucleus at the center. But instead of these orbits, we now have these what we call electron clouds. And what that means is that this cloud is the region in space that you will more than likely find the electron. So so this is where it gets a little bit complicated. You can't really say that electron is here at one particular point. You can say that, you will find it is 80% likely that you will find the electron in this particular location. 81% over here, 83% over there, or what have you. And so you have this cloud, this region of space where the electron, it's somewhere in there. We're very, very sure that it's somewhere in that cloud. But where specifically, that becomes something of a question. But you can also see but with the quantum mechanical model, you can see where those regions of omission are. As I said before, with the Bohr model, there are very discrete orbits where the electron can reside. Here we see that in these discrete discrete clouds. So those areas that are labeled nodes, those are the areas that the electron cannot reside in. Those are forbidden regions. The electron, just for that particular atom, the electron cannot have that kind of energy and still be bound to that atom. So that's a closer idea or a closer representation of what atoms actually look like. Well, like I said, for simplicity's sake, or simplicity's sake, but it's simpler for me, or at least I feel it is more straightforward to look at the atom as if it were the Bohr model. If it looks like this, where again, positive nucleus, and then electrons which reside on these circular orbit, on one of these circular orbits. Now, I'm going to refer to these as energy states. I'm going to refer to this circular orbit here, this orbit here, the one closest to the nucleus, that is the ground state. This is the first excited state. The shell above the ground state is the first excited state, and then the second excited state is above that, then the third, then the fourth, and yada yada yada, out until not really infinity, but out until a certain distance. Each of those energy shells corresponds to a very, very specific energy, meaning that if you want to go from ground state, the ground shell, to the first excited state, you need to give the electron a little bit of energy, as I'll demonstrate in a second. The main thing to keep in mind, there are two principles to keep in mind. The first principle is that energy is neither created nor destroyed. Any energy you put into the atom, you're going to get exactly that amount of energy out. It may not be in the same form, but it will have the same magnitude. You will have the same amount of energy coming out that you put in. The other thing, and this is a lesson that I think is this is a principle that is not stressed enough, is that nature is lazy. Nature wants to be in the lowest energy state it possibly can be. I refer to the ground state as the couch. Electrons want to be on the couch with a beer. They don't want to be bothered. They don't want to be pushed around. They just want to, if you leave them alone, they're going to go and sit down on the couch. It's only when you come and you bother them with energy, and they will pop up off the couch and they will go to higher energy states. But ultimately, unless you're continually bothering them, unless you're continually slamming this thing with energy, they're going to fall back down onto the couch. So those are the two principles that you need to keep in mind as we go forward. Chris, I am ditto. This is basically, when I think of the universe, I feel seen by thinking of the fact that, yes, the universe, like myself, is very lazy. So let's stop that. And so let's go to this handy dandy simulator. It's actually one of my favorite simulators. So what we have here is we have again, we have the proton. This is a hydrogen atom, but really this everything I've been showing you here can be scaled up to any particular atom that you're interested in. The helium atom, a carbon atom, oxygen, gold, what have you. Basic principles still apply. But for the hydrogen, we have the like I said, the proton in the beginning, or the proton in the middle, and you have an electron hanging out on the couch. All right. Now, as I've said before, the electron can only exist with certain energies. So each of these, the couch only has a certain energy. The first energy level above it has a certain amount of energy, and so forth and so on. So if I were just to fire just any old random photon at this hydrogen atom, nothing's going to happen. Basically, the hydrogen atom is just going to ignore it. The electron's going to continue to drink its beer on the couch. But if you shoot it with a very specific energy, I come down here specifically, and a photon with an energy of 10.2 EVs. EV stands for electron volt. Really, all you need to know is that it's a really, really small amount of energy, but it is a definitive, defined, discrete amount of energy. So if you hit it with precisely 10.2 EV, boink, the electron is going to bounce up. It's going to bounce up to the second orbital, or the first excited state, or second orbital. And then, if you were watching, it's going to bounce back. It's going to fall back down again. Boink. It's going to bounce up, and then it's going to fall down. This is not the scale in any way whatsoever. It's not the scale in distance, and it's certainly not the scale in time. In time, that transition back to the couch is split second. It's very, very short. It's on the order of microseconds. So, but it's going to fall back down. And hopefully, again, as you saw, pops up, and then when it falls down, a photon gets emitted. And I haven't been really paying attention too much with the simulator, but it will get emitted in any random direction. That way, doesn't matter. Any random direction it will get emitted. So the process of absorption is if you've got a hydrogen atom of a certain energy, meaning a certain temperature, then if it's cold enough, then all of the hydrogen atoms are going to be sitting there with their protons and then their electrons all on their couches. And then when you fire any kind of energy into that very cold cloud, if that energy has 10.2 EV, those photons with 10.2 EV are going to get absorbed by that cloud, by the atoms within that cloud, and then re-emitted. So that spectrum that we saw, those dark lines that we saw, that's essentially why those dark lines are there, is because a photon of a particular energy was sent in. It hit one of these atoms that are really not very excited. It sucked in, or that absorbed that energy. That energy then turned into essentially the energy of motion for the electron to pop up to a higher state. Because nature is lazy, it doesn't like being in an energetic state, so it releases that energy. Electron falls back down. The energy gets released out somewhere else. So, what I've been constantly showing you here is what we call a Lyman alpha photon. Or really, it is a spectral feature which was first identified by a dude named Lyman. I can't remember his first name. No, I can't see the chat, so let me put this over here. Principle of least action. Yeah. And Lyman saw other things as well. So Lyman alpha is Lyman alpha photon. Like I said, is 10.2 EV. You can also have what is known as a Lyman beta photon, which is 12.09 eV. And that bounces it up from the ground up to the second orbital. Now, energy can't be created or destroyed. And so when the electron gets bounced up to here, it doesn't have just one way of getting back to the couch, but two. So if I were just to pop this up here and wait, it can either go directly back down, which means that that 12 eV photon that got emitted or got absorbed gets re-emitted as it was somewhere else in the universe. Or what can happen is it can stutter step. It can drop down to the first orbital or first excited state and then down to the ground. So instead of one photon being randomly shot out somewhere, two photons get randomly shot out somewhere. One with a energy of approximately 1.9 eV, and the other one of approximately 10.2, which if you add them together will get you basically 12. Container. So the amount of energy going in has to equal the amount of energy going out. You can also, and we can continue to play this game, we can scale this up. So Lyman alpha is the first energy state, Lyman beta is the second energy state. I think you can guess Lyman gamma is going to be the third energy state. And this is going to cascade down. So the number of ways that it can re-emit a photon are in different increases. So it can go all the way down, or it can go down 2 and then down 1, like that. Or it can step down every energy level. And each one of those corresponds to a particular photon with a particular energy, which corresponds to a particular wavelength of light that you see or can see. All of these photons that I'm looking at are Lyman are in the ultraviolet part of the spectrum. So we don't actually observe when we look at the spectrums that I showed you before. We wouldn't actually see these lines. What we would see is the Balmer series. So let me see if I can do this in succession. So first I want to bounce that up to there. And then I want to shoot it with that. And that second one is what we call a Balmer line, a Balmer H alpha, or what we call H alpha. For some reason, Balmer is not B, Balmer is H, hydrogen. Probably presumably because it was the first, Balmer was the first one. They were the first lines to be seen. But that only works. You only get a H alpha line if the electron is already excited. So if I were to shoot just a normal H alpha line at this very cold, hydrogen atom, it's not going to do anything. Basically, the energy is not appropriate enough for it to kick the electron to a particular higher state. It's only if the electron is already at a higher state that it's going to respond to these H alpha photons, or really any of what we call the Balmer series. So I could go H gamma. H gamma is going to knock it up 3. So it goes from the first excited state to the fourth excited state, and then it can cascade down. So let me see if I can bring this up. So I'm going to stop sharing that. I'm going to share this. So here again, you can see here, these are the, I'm going to concentrate on the Balmer series, which is in black. So if you see a photon or an electron drop down from the second excited state to the first excited state, that's going to emit a photon of a certain amount of energy, which corresponds to a wavelength of 656 nanometers, H alpha. The transition between the third energy state, third excited to first excited, that is 486 nanometers, and then so forth. So you can see that these nanometers correspond to the wavelengths of the light that gets emitted if the electron drops down, or gets absorbed if the electron pops up for each of these. Let me actually do this. Hydrogen. Actually, let me do function spectrum. Images. All right, boom, that one. I like that one. That one's nice. Make it nice. Here we go. There we go. So let me see if I can make that a little bit clearer. Bigger. Haha, yes, I will accept your cookies. So here are the absorption lines. So let's look at, and of course, the one I've been talking about is hydrogen is, of course, not on here, but each of these lines corresponds to, like I said, has a very particular wavelength. So imagine hydrogen is actually on here. If we were seeing hydrogen, what we'd see is at 556 nanometers, which is about right there, we would see, or 656 nanometers, sorry, right about, there, we would see a dark line right here. And then for hydrogen beta, or for H beta, we would see a teal line in or around this area. And then we'd see a couple of lines in the blue. Those, as I said, and I'm trying to stress this, those correspond to very specific wavelengths. And no other atoms have those wavelengths. So let's look at other atoms. Here we have helium, oxygen, neon, argon, and xenon. Let me get this over here. That way I can see the chat. You can see that each of these elements has an absorption pattern that is different than all the other ones. And not only do they look different, but if you were to analyze them, they are very different. They are uniquely different in that none of these lines, even though you might think that in this forest of lines here, you might get a line that's kind of in the same, that neon and argon actually absorb at the same frequency or same wavelength. No. Neon absorbs at very specific wavelengths. Argon absorbs at very specific wavelengths that are not the same as neon. This corresponds to a chemical fingerprint. So if I know, and this is where the work, where astronomy is done in the lab, really by physicists. It was, I don't know if it still is, but it was a very robust field of study for people to get into the lab, take these elements, and then heat them up to certain temperatures to see where these absorption lines were located, where either absorption or emission lines were located, and they would go through and they would catalog all of them. So this is only in the visible part of the spectrum, the part of the spectrum that you can see with your eye. But this also happens, these lines also occur in the ultraviolet, in the X-ray, the gamma ray, the infrared, the radio, everywhere along the electromagnetic spectrum, you have a chance of finding a line if the atom is particularly sensitive to that photon of that energy. So, if we have an unknown gas, if we look at a star or a nebula or some kind of object, we will get an absorption spectrum like this. The reason why we can tell you that particular element, that particular nebula is made up of hydrogen, helium, and what else, is because we can look at the spectrum and then we can compare. So, all right, if I go to here, we got helium there, that looks good. Go over here, that line is there, this line is there. This line is actually helium might be a little bit. No, it's not helium because actually this is a great example. This may look similar. This may look similar, but this one doesn't match. So helium isn't there. It's definitely not oxygen. It's definitely not neon. It's definitely not argon. And finally, we can say that this unknown gas is actually xenon. But the universe is more complicated than that. What we find is that if we look at any particular gas, it's going to be a superposition. It's going to have more than one thing. So if this were really in everyday, if this were an astronomical object, more than likely it would also have the spectrum of helium superimposed onto it and the spectrum of hydrogen superimposed onto it. And so basically by looking at all these lines, we can then compare that to the database of lines that we have discovered in the lab, and we can identify which chemical species reside in any given object, gas, solid, what have you. Are those absorption lines similar to when you have a laser and you see black lines between the colored lines, like black line, red line, black line, red line? I don't believe so. Although I'm not quite certain what you mean by that. What reading that, I'm guessing what you're referring to is what's known as an interference pattern. Something that you would get when you pass light through a slit and the light diffracts and interferes with itself. You would get bright lines, dark lines, bright lines, dark lines. I suspect that's the phenomenon you're describing, which would not be this. Diffraction grating effect, maybe. Diffraction gratings will give you this. Are used for astronomical spectroscopy. So that's how we like I said, that's how we identify chemical species in the universe. That's how we know that the sun, for example, is primarily of hydrogen and helium. And incidentally, helium was first discovered in nature in the sun. It was hence why it's called helium. Helios, sun. The element helium was not discovered on the Earth first. It was actually discovered in the sun before it was discovered anywhere else. I was able to parse it, so you explained it well enough. So yes. So let's go back to stop share, present my handy dandy element. So there are a couple of things that I want to focus in on before I move on to the Doppler effect and I've already kind of hinted at this or sort of referenced it in a way, is that the lines that we see. So another thing that I've just described how we use spectra to determine whether or not there are chemical elements. What chemical elements can we find in the atmosphere of the sun? But we can also go a little bit further. We can also ask the question, what temperature is the surface of the sun? And we can do that because, if we find that we look over a broad band. If we look over, say, the infrared, the visible, and the ultraviolet, we fire a photon here, and we look at the ultraviolet. We see a Lyman alpha line. All right, that tells us that that hydrogen exists. But what if we find in a gas, and this is a hypothetical gas, nose, hypothetical gas, we find Lyman lines but we don't find Balmer lines or Paschen lines, which requires you to be all the way up here for that to work. What that tells you is something about the temperature, at least to first order. I mean, it gets more. We have more sophisticated methods to determine the temperature more precisely, but just from a just kind of like a first order, first blush approximation. If so, like I said, the electron is going to be in the lowest energy state it can possibly be. If the gas is cold, if it's in a cold environment, if there are not a lot of photons going around, then most of that hydrogen gas is going to be in the ground state. It's going to be right. It's going to be right there, as you see it, and so it can be activated by Lyman photons, but it cannot be activated by Balmer photons or Paschen photons. So if we see a certain lines in there, we know that the gas must be in a certain energy state in order for it to, if we can see, for example, that hydrogen is there, we can see the Lyman lines, but we can't, for whatever reason, see the Balmer lines. That tells us that the overall gas is at such a low temperature that most of the gas isn't in a position to respond to those Balmer photons. Hopefully that makes sense. And so we can look at the ratios between the Lyman series of hydrogen lines and the Balmer series of Lyman line or Balmer series of hydrogen lines. And by looking at the ratio between them, we can get a temperature of the gas. So if, for example, if we were looking at this and we were getting very little Lyman lines, if we were going at this gas and we saw the Lyman alpha line was very faint comparison to a Balmer alpha line, what that means is that most of the gas is actually like this. Most of the gas has the electron already excited, and there's so much energy going around, or there's enough energy going around, enough energetic photons going around, that every time the electron considers going back down to the couch, it gets popped back up again. So if you were to take a random sample of hydrogen gas and say, what state is it in? If you see a whole bunch of Balmer lines, but not a whole lot of Lyman lines, then that tells you that most of the gas is going to be slightly excited. And hopefully you can see that that if you see a whole bunch of Paschen lines, where the Paschen lines, but not a lot of H. Balmer lines or a lot of Lyman lines, then again, you know that the electron is most likely going to be in an excited state, which implies a hotter environment. So the gas is at a higher state. Last thing, I need to quit messing with my nose. And and the last thing to really say about this is there is a limit to how much energy an electron or an atom can be hit with. So if I were to go over here and smack it with a 15 eV photon, pew, electron goes flying. We refer to that as photoionized. Basically, I have hit it with so much energy that the electron is now free to go. It has now basically reached escape velocity and has now become unbound to the proton. Specifically, that corresponds to an energy of 13.7. So if I were to go just a little bit before then, a little bit under that, I'll let it do its thing. If I did a 13.6, oh no, actually, I got that wrong. It's 13.2. Yes. 13.2. Sorry. 13.2. I could have sworn. I will have to double check, and I will come back on to find out exactly what the photonization energy of a hydrogen atom is. I could have sworn it was 13.7. But you get the idea. There is a certain upper limit. Under that limit, then the electron or the hydrogen atom, the electron will bounce up to a higher state, but it will still be bound to the photon, or the proton rather. 13.2, yes, 13.22. That's the photonization limit. If it's slightly higher than that, it'll bounce off. Yes, actually, we can. And we know that at least the moon of Titan is made up, one of its constituents is ethanol. So, yeah. So, yes, we can in fact tell if a planet is in fact made up of alcohol. Specific alcohol? I don't know. I'm not that well versed in chemistry. Probably, I would say yes, but yeah. So astronomers can tell you the best places in the universe to get drunk just by standing in its atmosphere. That is really what I'm most proud of as an astronomer, is we can tell you where to best get drunk. So hi Judy, howdy. So yeah, so that's the basics of the hydrogen atom, or basically that is how absorption and emission happens. Just to recap, if you hit, depending on so an electron is going to reside in an orbit or orbital around the proton. Depending on where that is, where that electron resides, then a photon of a given energy comes in, and it's going to react. It's going to absorb that energy, causing the electron to bounce up to a higher state. And then it's going to re-emit that energy in some random direction when it's lazy and gets back down to its energy state. All right, so yeah, that basically that wraps up the Bohr model of the atom and how emission and absorption works. And like I said, we can use this sort of information to determine not only just the chemical composition of a gas, but also its temperature as well, along with other things like density. And it's really amazing what we can extract from a spectra. All right. So now let's talk about the Doppler effect. Hopefully you're all familiar with the Doppler effect. We use it in weather. We're really the best, actually. My father was a nurse, and he did research studies for congestive heart failure patients, which is really just, it's not pleasant. Anyway, one of his patients was an Aussie, as I've been told, and he gave my father this thingamabobber, which I am probably going to break something doing this. So let's see how badly this goes. Actually, let me not use my arthritic hand to do this. Let's try that again. I don't know what it's for. I don't know what it's used for. I don't know if you heard it, but it makes a whirring sound. As the thing goes around, it makes a whirring sound, and it kind of go, and you could hear it go. What I was trying to demonstrate with that silly experiment is the Doppler effect as we normally experience it here on Earth, which is via sound. If something is emitting sound and is coming at you, the frequency of that sound is going to appear or is going to seem to increase. And then as the siren moves away from you, the frequency is going to drop, or the pitch is going to drop. Same thing happens with light. And we can use propeller sound. Yeah, all right. So apparently it was audible in some way. So we can use that effect to our advantage in terms of light, because we can use that to basically look at motion, to analyze whether or not something is moving in any particular way. So if you remember, that we had those, with the spectrum, you have these absorption lines or emission lines, but let's take the example of absorption lines. They correspond to very specific wavelengths. As I said, that's the chemical fingerprint due to the internal mechanics of, or internal physics of the atom. So, if the Doppler effect means that depending on something's motion, the frequency and or wavelength changes, then we should be able to see that in the spectrum and then reverse engineer it. So, let me do this. Share screen. Doppler. That one. That one. So let me pull this out. There we go. All right. So this is a really simple picture of how we use this. So let's imagine we have a galaxy. It's obviously composed of stars and things that emit light. So that light is being emitted in all directions, represented by these circles. We got the Earth over here. We can run this. And so right now, the galaxy is moving away from us. Now I'm actually going to reverse it. Oh, no. All right, let's start this where the galaxy is not moving relative to anybody. So we'll just wait. Propeller sound, best propeller sounds in the North American AT6 Texan Harvard. I'm going to go with that's a plane that I'm not familiar with. All right. So now that the simulation has reset itself, we have the Earth, as I said, on the left, and we have the galaxy on the right. The circles represent basically light emitting off of that galaxy in all directions. That wavelength that you see, that sinusoidal wave, corresponds to the wavelength of any particular bit of light that we happen to be looking at. So if the galaxy and the Earth are stationary relative to each other, then the frequency or the wavelength of the light that is emitted is exactly the same as the wavelength that we see. So, for example, you have an H alpha line being emitted by the galaxy. So you have a light which has a frequency, a wavelength of 656 nanometers, and it is being emitted by this galaxy at 656 nanometers. If there is no motion between the two objects, then we will see that light from that galaxy at 656 nanometers. But if the galaxy is in fact moving towards us at a fairly high rate of speed, what we can see is that every instant, every second it emits light, it does so, and then the galaxy moves relative to where that light was emitted. And so the wavelengths, as seen as it goes towards the Earth, get shorter. Essentially, the waves stack on top of each other. You can think of it in that way, is that the waves, basically the galaxy is outpacing, or not outpacing, but is traveling with a velocity, is traveling with a certain velocity, and so it's stacking the waves on top of each other in a way. I know there's a better way of explaining that. Hopefully visually you see it. You notice that with the wavelengths getting shorter, that means that the frequency goes up, the energy goes up, the wave gets, or the light gets bluer. We refer to that as a blue shift. If the galaxy is moving away from us really fast, then here the opposite is happening. So so when it emits out a pulse, the galaxy is going to move over to the side, and so the wavelengths, as they are seen from the Earth, appear to get longer. And so that means the longer the wavelength, the frequency drops, the light gets less energetic, the light is redder, hence a redshift. And so that is what we mean by blue shift and redshift. If we measure this, what we would measure is that the 656 nanometer line, as we see on Earth, would actually be seen from this galaxy at 660 nanometers or 670 nanometers. And the size of that shift is directly proportional to the velocity of the object relative to us. So bigger shift, bigger velocity. But let's look at this with a little bit more depth. Nope. 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 All right. Where'd he go? This one. That's the one I want. So stop. Sent. Share screen. Foothill. All right. Hopefully you all can see that. That is an excellent question. And yes, we do. So if Hubble, for example, had actually, is that fair to say? Yes, yeah, it is fair to say. Hubble, if you look at just the Andromeda Galaxy, the Andromeda Galaxy actually has a blue shift. What that tells us is that the Andromeda Galaxy is approaching the Milky Way galaxy. Is that they are gravitationally attracting one another and are moving closer. So in about 4.5 billion years, give or take, the Andromeda Galaxy and the Milky Way galaxy will begin to merge, will actually fall into each other and go through a very complex merger process. So yes, we do see a few galaxies with a blue shift. Now, most of the galaxies that we see are in fact redshifted. And that tells us that, in fact, the reason for that is because the universe itself is expanding. And at certain distances, that expanding velocity is larger than any peculiar motion, which would basically, which would indicate individual motion. Like, for example, so as I said, Andromeda and Milky Way galaxy are gravitationally bound. There's a certain peculiar motion which is drawing them towards each other. But if the Andromeda galaxy were further away, then the expansion of the universe would be large enough that we would essentially not be able to see that blue shift. That it would actually it would be moving away from us, but it wouldn't be moving away from us as fast because it was coming towards us. If that makes any sense? Hopefully that makes sense. But yes, to answer your question, if the galaxy has a high enough velocity towards us and is close enough, then yes, we will be able to see a shift in the. So here, what we have source, green source, red observer. And so indicated by these lines. So you have the green line, which corresponds to the to the source. You have the red line, which has nothing to do with redshift. It's just a red line to indicate the observer. So what we can do here is I can pick up the source and I can move it. I think I can move it. Oh, wrong screen. Whee! You can see badly that as the source, when the source actually, the observer measured the light as being scrunched, as being redshifted from the source. And then if I move away, you can see that the light gets longer, blue shifted, red shifted, or blue shifted before, now it's red shifted. The light gets, waving on it gets longer, the light gets redder if I move it away. So again, blue shifty, red shifty. But as Einstein would tell us, everything is relative. So you get the same effect if the source is moving or if the observer is moving. So if the observer is moving closer, you can see that the wavelengths get shorter, light gets bluer. If the observer is moved away, basically it's trying to run away from the light, wavelengths get longer. So the Doppler shift, or the red shift, the shift of lines is, or the Doppler shift, I should say, is independent of, or has no absolute frame, in the sense that it doesn't matter when you measure the Doppler shift, you're not measuring the absolute velocity that something is moving away from you, or something is moving towards you, or even that you are moving towards it or away from it. All you can say with the Doppler shift is that the relative motions between the two objects are coming towards each other or they're going away from each other. It says nothing as to which one is fixed, or which one is freely moving, or even if you're measuring a shift of 60 or a approaching velocity of 60 meters per second, it doesn't. It says nothing as to whether how fast each one is individually moving. It only tells you that those two objects are coming at each other, or appear coming at each other, at 60 kilometers per second. So it is a relative effect. The other thing that red shift, blue shift, what have you, Doppler shift anyway, tells you is that it only tells you the velocity in the radial direction, the direction directly towards you and directly away from you. It cannot tell you what the speed of something is in what we call the transverse direction, or left or right. Not really, anyway. Because the Doppler shift only has to do with motions that are directly towards or directly away. If you move left and right, essentially that will really not cause a shift. I mean, it will because of the geometry of the situation, but effectively it won't. It only, you really, let me rewind that. The Doppler shift can, like I said, can only tell you the direction radially, whether or not how fast something is moving away from you or how fast something is moving towards you. It really can't tell you how fast something may be going around you, say moving left or right. So a Doppler shift. So when I say that the Andromeda galaxy, and this is just a made-up number, but say the Andromeda galaxy was moving towards us at 60 meters per second. All I can say from the redshift is that it's moving towards us at 60 meters per second. It tells me nothing about whether or not the Andromeda galaxy is also moving to the left of me or to the right of me, by any stretch. So I can't say the overall velocity of the Andromeda Galaxy is 60 meters per second. Only the to and fro velocity. In order to get the other velocity components, you actually have to use different kind of techniques. So yeah. So there's that. All right. Let me see if I can see if there's anything. All right. I think there's another question. Interesting. I would have thought everything would be redshifted to the claim that the universe is expanding. So things further away accelerate, blah, 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 but not. So things further away accelerate, expand more than things that are closer, and not at all the same rate of thought. So think of it this way. If you've got, all right, how would I put this? So nothing in the universe is stationary. You always have some kind of motion. Galaxies have some kind of motion, and that motion is essentially random. It's that motion is dictated by really the initial conditions of how the thing came into being, how it formed, how the star formed, that sort of thing. So basically you can wave your hands and say it's random. And any object is going to have a velocity in any different direction, and it's going to have a velocity of a certain magnitude, but only up to a certain, like, it's not going to, it's going to have a certain range in velocities that it can go, that it can be from initial conditions. But it's going to be really peculiar if it's a really high initial velocity. At some point, what we call the proper motion of something, the intrinsic, just random motions of an object, are going to kind of max out at some range, as it were. So if I've got let's say you take a balloon. Let's go this way. Let's say you take a balloon that's relatively deflated, and you put dots all over it. Then you start filling it up, filling it in air at a certain rate. And so the balloon is going to expand at a certain rate. That is the best example I can give you of what we call the Hubble flow, or the expansion of the universe. And so the distances, if you were to plot on all, I think I went too fast. Take a deflated balloon, put dots all over it, measure the distances between those dots, and then start inflating the balloon, and then continually measure those distances as the balloon inflates. Those distances are going to change as a function of time. That gives you a velocity, and those velocities are going to change based on how far away those dots are from each other. So that is the best example I can give you of the Hubble flow. But the underlying assumption with that example is that all of those dots have no peculiar motion, have no proper motion in and upon themselves. They are fixed to the balloon. In reality, they're not. In reality, stars, galaxies are not fixed into space-time. They are moving with their own peculiar velocities. And so, and in this case, well, in all cases, velocities add. So if I am coming towards you at 60 meters per second, but I am far enough away from you that the universe wants me to expand at 30 meters a second away from you, then you would see me as moving 30 meters per second away towards you. So if my natural motion would mean that I am moving towards you at 60 meters per second, but the universe is causing me to expand and move outward at 30 meters per second, then I'm actually going to be moving towards you at 30 meters per second, 60 minus 30. So for stars or for galaxies in the local group, the closest galaxies to us, the dozen or so close, about, I think it's 24 at last count, 22, 24, somewhere in there. For those galaxies that are closest to us, the proper motions of those galaxies, those motions, those intrinsic motions to the galaxies that they were sort of born with, they are larger than the expansion of the universe. The velocity is imparted to them by the expansion of the universe, so we can see blue shifts. If you get out to if you start talking about distances like 100 megaparsecs, then the velocities due to the expansion of the universe start getting into the tens of thousands of meters per second, which far and again are far larger than any of the individual motions they may have been born with. These peculiar motions typically are on the order of maybe hundreds of meters per second, as opposed to tens of thousands of meters per second. So yeah, I don't know if that answers your question, Rachie, but yeah. So when we talk about the Hubble flow and the expansion, we are basically neglecting the fact that things have their own individual motions. And yes, that is true. Oh, relativistic time dilation? Yeah. I like to look at that in terms of actually redshift. Gravity redshift. That's beyond the scope of this. But yeah, gravitational redshift. Or gravitational redshift, yeah. I don't really like thinking, I don't tend to think of it in time more as in energy, as an energy phenomenon rather than time phenomenon. All right. Well, that is excellent. Right. All right. Well, that is all I have for you today. So let's see what's coming up next week. So next week, I am going to be. We're going to be moving on from light to telescopes. Woohoo! I get to talk about one of my favorite things in astronomy, something that I get to play with all the time, which is telescopes. I will talk about telescope designs. I will talk to you about detector systems. How is it that we measure? How do we take data? What does our data look like? How do we extract data from those images or that material? So forth and so on. So yes, I will be getting into telescopes and that sort of thing. So that's gonna be all of next week. So now I am done with light. So if you have any questions, feel free to pop them up in the chat or in the comment section. I think I'm a little bit behind on some of the comments in some of the other videos, but I do try to get to them as quickly as I can. And if not, you also free to email me at I just put in the chat my personal email address. You can also find it on my About page. So if you have any questions, if you watch this video and you have any questions either later or basically not now, feel free to email me if you don't want to put them in comments. So, as always, if you like this sort of content, please like, share, and subscribe. If you'd like to support what I do here at the university, specifically in outreach, consider becoming a patron of mine. All proceeds go to helping us with our outreach efforts, which includes, and one of the reasons why I'm kind of having to wrap this up, is that I am going, and Planetarium and three of my minions, tour guides, we are going to Navy Elementary School in Fairfax with the Planetarium, and we're going to do a STEM presentation, or we're going to be part of the STEM festival kind of thing. And yeah, I get to show elementary school students the Planetarium. So real excited about that. Hopefully they don't use my planetarium like a bouncy castle, which some have done in the past. But so yeah. So yeah, if you consider helping with that, like I said, please consider a patron. So what else can I say? I wanted to say something else too. We just fixed our telescope. I broke it and we fixed it. Basically, I tried to improve it, and I burned out the motherboard of our control computer, and we just got it. We just basically fixed it. We had an old computer, a backup computer. We got it back up. And so where I was going with that is I'm hoping that I can steal some time fairly recently to actually do a live stream with the telescope and show you what taking images looks like and so forth and so on. I've got a couple of live streams on the channel where I do that, where I've done that in the past, but I haven't done it in a while. And I figure I should, I owe you guys some live views of our telescope, particularly if you can't make it out here in person. So, oh yeah, I bought duct tape because with Judy's money, actually, I bought some duct tape. Let there be no more. Yeah, frequently when I try to improve things, I break things. They tell me that's actually a good thing, but I don't know if I believe them. What is the U in that equation? U is I don't. You find the weirdest ways of writing equations. I kind of know it because I don't know what U means in that context. I should know what U means in that context. Anyway, it's relativistic. I know there's the Lorentz factors in there, but for whatever reason, I can't seem to parse that. Okay. Velocities U and V. All right. Yeah. Okay. Yeah. So U is a velocity. That makes sense. Oops. All right. So yeah. I keep saying yeah. Thank you all for being here. I hope that you found this entertaining. I certainly hope you found this educational. Like I said, next week I'll start talking about telescopes. So until then, I am off to go show little people the stars. Be good. Peace out. Clear skies. And I'll see you next time.